the function e power x from R to R is smooth and strictly increasing. Its image is 0, infinity. We have seen all these aspects in the module on the exponential function. Therefore, we can apply the inverse function theorem to conclude that there is an inverse differentiable inverse, in fact C1 inverse from what we have already seen. There's a C1 inverse such that, or rather C1 inverse f from 0 infinity to R, that is also strictly increasing. Again, every single statement that is made in this paragraph can be easily justified using the content that's already been developed. So I'm going to leave it to you to check this in its entirety. Okay. Moreover, we have that f composed with, or rather let me directly compute the derivative. F prime at a point y is nothing but 1 by exponential of f of y, right? The inverse function theorem tells you how to compute the derivative of a function also, right? So the derivative at y of the inverse of the exponential function will be nothing but 1 by e power f of y. Okay. Now exponential and this function f are nothing but inverses. So this is nothing but 1 by y. Okay. So we have got that the derivative of this function, the derivative of f is 1 by y at the point y in 0 infinity. Okay. We also know that this function f must satisfy f of 1 is equal to 0, simply because exponential at 0 is 1. Okay. Now we already know that f is strictly increasing, and it also satisfies this nice identity that f of xy is equal to f of x plus f of y. How do you show this? Well, it's very similar to how we showed a similar property for exponential, that exponential of ab is exponential of a plus b is exponential of a into exponential of b. You can use that to prove this, or you can prove this directly by considering the function. So fix a, this proof is going to be very similar. Fix a in 0 infinity and consider the function g of ax minus g of x. Consider this new function, differentiate this function. Well, by chain rule you will just get 1 by ax into a minus 1 by x, which is 0. This just means that g of ax minus g of x is just constant, is just some constant. Now set x equals 1, we get g of a minus g of 1, which is 0. So we get g of a is this constant c. Okay. In other words, g of ax is just g of a plus g of x. Okay. Now again we can just consider g of a squared and we will get 2g of a. And similarly by induction we get g of a power n is equal to n times g of a. Okay. Now because g is strictly increasing, remember I wrote that back, g is strictly increasing for a fixed a greater than 1, we note that star gives that g of a power n as n goes to infinity diverges to infinity, right? As a power n, as you keep boosting a, if a is greater than 1, of course g of a is not going to be 0, because we know that g is strictly increasing and the fact that g of 1 is 0. So g of a power n is n times g of a. So as n goes to infinity, g of a power n converges to infinity. But g is strictly increasing. That just means that as x goes to infinity, g of x converges to infinity. Okay. So this function g is strictly increasing and it goes to infinity as x goes to infinity, and at the point 1 it's going to be 0. Okay. Furthermore, if x is greater than 0, then 0 is equal to g of 1 is equal to g of x plus g of x inverse, right? This is just coming from the identity that g of xy is g of x plus g of y, right? So which means g of x inverse is equal to minus g of x. If x is greater than 1, then this means g of 1 by x is going to be minus g of x, which is going to be negative. Okay. And since as x goes to infinity, 1 by x goes to 0, and g of x goes to infinity, g of 1 by x goes to minus infinity. Okay, because g of 1 by x is just minus g of x. So this function g is nothing but the logarithm, but the function log from 0 infinity to r. Okay. Now we have shown several properties of the logarithm, but we still do not have enough data to draw its graph. For that we need the second derivative. Clearly the second derivative is of log y is minus 1 by y squared. We already know this because the derivative is 1 by y. So this has got to be when y is greater than 0, minus 1 by y squared is less than 0. This means the function log is concave. Okay, it's concave. It's not concave, sorry. It's not concave. It's convex downwards. It's convex downwards. Okay, what this means is that the function essentially looks like this. A familiar picture of the logarithm function. Okay, So we have established in record time all the basic properties of logarithm, essentially covering years of your school syllabus from middle school in a matter of 10 to 15 minutes. Let's now proceed to something newer. So if a is greater than 0 and x is any number, we can now define a power x. We can now define a power x to be e power x log a. This is a long pending definition. We had made this earlier, but without the existence of the exponential and logarithm done in great detail, this definition will not really make sense. Now notice that by the properties of exponential and logarithms, this agrees with the usual definition of a power n when n is coming from the integers. Okay, so this is not something entirely pulled out of the air. This is a sensible definition. Okay, I am going to just prove one property of the logarithms that is really nice. Theorem, let k be a positive integer, then limit x going to infinity log x power k by x is equal to 0. We already know that the exponential function goes to infinity faster than any polynomial. We have encountered this phenomenon several times in this course. This is saying something interesting. Take the logarithm, we know that it goes to infinity. Boost the speed at which it goes to infinity by taking power k. It still goes to infinity far slower than even the linear factor just x. So the logarithm function grows really slowly, and that is captured quantitatively and analytically in this theorem. And the proof is fairly easy because we have already done the hard work using the exponential function. So what you do is you set x to be e power z. In other words, z is just log x. Okay. Then log x power k by x is nothing but z power k by e power z. Okay. Now when x goes to infinity, so does z. But by the earlier result, limit z going to infinity, or rather x going to infinity, z power k by e power z goes to 0. Okay, as required. Okay. Now there's an easy corollary of this, which I'm going to leave it as an exercise. Show that limit x going to infinity x power 1 by x is equal to 1. And recall that we have shown something similar to this for sequences. Okay. Now we end with yet another proof of a famous limit form for the exponential. What we do is the following. We know that the function log is differentiable. That's how it was constructed as an inverse of the exponential function. We essentially created the log function using the inverse function theorem. Therefore, it's differentiable. At the point 1. The derivative is given by the limit h going to 0 log 1 plus h by h. Okay, and this is nothing but limit h going to 0 log 1 plus h minus log 1 by h, okay, which is just 1. We know this because the derivative of log is 1 by x or 1 by y, and y in this case is 1. Okay, now log 1 plus h by h, log 1 plus h by h is nothing but log 1 plus h power 1 by h. Okay, so log 1 plus h by h is nothing but log 1 plus h power 1 by h. Check this. This essentially follows from the basic property of the logarithm and the way we have defined exponentiating with respect to a real number. Okay, now taking logarithms on both sides immediately gives limit h going to 0 of 1 plus h power 1 by h is just e. Okay, so this is yet another way of seeing this famous limit. This is a famous limit. Okay, so these are some basic properties of the logarithm functions. There are some more in the exercises. This is a course on real analysis, and you've just watched the module on the logarithm.